So we discussed the eigenvalue problem and how to solve a modal analysis. Now we pose the question, is every natural frequency equally important? For a realistic model, we might have thousands or millions of degrees of freedom, which means that we can find that many natural frequencies. Have a look at this drone. It is made of hundreds of parts, and when meshed with the finite element method, there can be over 1 million degrees of freedom. That's 1 million natural frequencies and modes. Is it necessary to find them all? Are they all important to the same level? The answer is no. In most cases, as we discussed in the preceding lesson, the high frequency modes are typically negligible. And not every mode participates to the same level of deformation of the structure under dynamic loading. So how do you determine the sufficient number of modes to extract, and how to find the most important natural frequencies or modes? To quantify these, we use two simple scalars, mode participation factor and effective mass. Mode participation factor measures the amount of mass moving in each direction for each mode. A high value in a direction indicates that the mode will be excited by forces or excitations in that direction. Let's see how the participation factor and effective mass are calculated. Essentially, we take the transpose of the mode shape or eigenvector matrix phi, multiply it by the mass matrix M, and then multiply it by the excitation direction vector D. This vector D represents the direction the participation factor is calculated in. Now the effective mass is mathematically just the square of the participation factor, and in some textbooks and articles, the effective mass shown here is called the participation factor. But participation factor and effective mass serve very similar roles in modal analysis, and the engineer will typically look at either of them to gain an understanding of the significance of the particular mode. Let's have a look at the modes for this particular drone. Arbitrarily, we extract 12 modes for this structure. The data table shows the natural frequencies, as well as the participation factors and effective mass calculated in the z direction. So it is in the z direction because the unit vector representing the z direction was used in the equation. Mode 1, 5, and 11 are contributing significantly to the deformation in the z direction. We see this as they have the highest magnitudes for their participation factor and effective mass. This means that they are most easily to get excited in vibration excitation in the z direction. In doing modal analysis, we should include most of the significant modes, meaning we should extract a significant number of modes to evaluate. This can be judged by the ratio between the effective mass to the total mass. If the ratio of effective mass to total mass is close to 1, it means most of the significant modes have been extracted. In this case, 12 modes are extracted. The ratio of the effective mass to total mass reaches around 0.88. Now the only way to get to 1 for the effective mass ratio is to include all the modes, but in most linear dynamic modal-based simulations that will utilize these results, 1.0 is unnecessary. What number is sufficient often depends on the type of simulation and the established engineering guidelines, but typically shooting for the ratio to be greater than 0.9 can be common. So let's have a look at the calculation of the mode participation factor and effective mass for our simple 2 degree of freedom spring mass system. We have the eigenvector matrix phi from the modal analysis, which we solved in the preceding lesson. We do a simple transpose on it and multiply it by the mass matrix and the excitation direction vector D. The excitation direction vector D in this case has 1 for both values, as we only have degrees of freedom in the y or vertical direction, and we are looking for the participation factor in that direction. Now if there were other degrees of freedom that the masses could move in, and we were interested in, say, the different directions, say participation in the horizontal direction, this vector would be changed accordingly, such as putting a 0 to not include a vertical degree of freedom with a horizontal excitation direction. Finally, we easily compute the effective mass. We see that the first mode we are exciting the majority of the mass of the system, giving us 2.94 kilograms, compared to the total of 3. The second mode excites much less of the total mass of the system at only 0.05 kilograms, and the total of these equals 3 kilograms, which is expected since we have 2 degrees of freedom and we have extracted all the modes.